So, hello everybody. Now we start our afternoon session. And for the invited talk, we are very fortunate to have Daniela Kühn from the University of Birmingham. And she will tell us how she and her team proved a conjecture about graph coloring that resisted half of the century before. Please go on, Daniela.
Okay, so thank you very much for the invitation. So the talk is about the Erdős-Faber-Lovász conjecture, and it's joint work with Dong-Yeap Kang, Tom Kelly, Abhishek, Methuku, and Deryk Osthus, all of whom are at Birmingham. So the Erdős-Faber-Lovász conjecture is a conjecture about graph colorings, and this means that you have a graph, and what you are doing is you color the vertices of this graph. But the property you want to achieve is that whenever you have two vertices which are joined by an edge, then they should get different colors. Okay? And the chromatic number is just the minimum number of colors with which you can do this, and it's denoted by chi. And now what does the Erdős-Faber-Lovász conjecture say? It says that if you have a sequence of graphs, of n complete graphs, such that each of these graphs has at most n vertices, and such that whenever you look at two of these graphs, they intersect in at most one vertex. Then you can color the union of these graphs with n vertices. So if you look at this picture here, we have one graph which consists of 4 complete graphs, and each of these complete graphs has size 4, and we have colored the union entire graph with 4 colors. Okay. Now, Erdős-Faber-Lovász, they actually formulated this at a tea party at a conference in Boulder. And at the beginning, they thought this is some toy problem, and they should be it should be easy to solve. So they expected it to be solved in the afternoon, or at the very least on the next day. But it turned out to be a bit harder than they thought, and so Erdős actually offered an increasing amount of prize money for the solution of this conjecture. So starting with $50 and he raised it in the end to $500, and he actually wrote that he considered this as one of his three most favorite combinatorial problems. And what we did is we proved this conjecture for all sufficiently large n. Okay, now there's also a more general version. Again, you have n complete graphs, and each of these complete graphs has at most n vertices. But this time, whenever you look at two of these complete graphs, they can intersect a bit more. So you're only restricting yourselves to the property that the intersection is at most n t vertices. And then the question is, again, you want to color the entire graph, the union of all these complete graphs. And the question is, how big can the chromatic number be? So this is due to Erdős, and the Erdős-Faber-Lovász conjecture would deal with the case when t is 1. And it would, the answer there is conjecture to be n. Okay, and we proved that if t is not too big, so if t is at most square root n, then the answer is t times n. And this is tight, because there are infinitely many examples where when you look at the union of these graphs, what you get is one big complete graph on Tn vertices, and then of course its chromatic number is Tn. And now this only works if T is at most square root n, but actually this is not a real restriction, because some earlier result of Horrocks and Tusa shows that after this, the chromatic number of the union of all these cliques doesn't grow anymore. So it's always at most n to the 3/2. Okay, so basically this settles this question of Erdős again for large n. Now, I formulated this Erdős question, also the Erdős-Faber-Lovász conjecture in terms of graphs. But it turns out that if you work on it, it's helpful to think of this conjecture in terms of hypergraphs. So actually, this conjecture has a version in terms of a reformulation in terms of hypergraphs, which I want to show you. But before I do this, I would like to introduce some terms about hypergraphs, because obviously we need them. Now, if you have a graph, you have vertices, and some of these vertices are joined by edges, so every edge has size 2. In a hypergraph, you allow the edges to have size also bigger than 2. So, for example, if you look at this picture on the right here, every edge has size 3. Okay, so all these things here are hypergraphs. In particular, a graph is a hypergraph. Apart from the fact that the middle one is a multi-graph, and so this is a multi-hypergraph. So multi-hypergraph is just a hypergraph where you allow multiple edges. Now, if every edge of your hypergraph has size k, then we call it k-uniform. So if you look at graphs, then these are 2 uniform hypergraphs. And if you look at this thing on the right, every edge has size 3, so it's a 3 uniform hypergraph. And the last thing we need is the notion of a codegree. And this is, well, you look at any 2 vertices in your hypergraph, and then you count the number of edges containing these 2 vertices. That's the codegree of this pair. So if you do this for graphs, where you don't allow multiple edges, well, then any 2 vertices only lie in at most 1 edge, and so the codegree is 1. But for hypergraphs, you can get bigger codegree, of course. Okay, and we will be talking about edge colorings of hypergraphs, not vertex colorings. And so we also need to talk about matchings. Now, a matching is just a collection of edges which are pairwise disjoint. So you don't want to have edges which intersect in 1 or more vertices. Okay, and an edge coloring of a hypergraph is when you give the edges of your hypergraph colors. But the property you want to guarantee is that whenever you have 2 edges which are not disjoint, then they should get different colors. And so this means your task is you have to look at the entire edge set of your hypergraph, and you want to split it into matchings, because then every matching you can color the same. And so you have an edge coloring of your hypergraph. Okay, and the chromatic index is just the smallest number of colors with which you can do this, and we denote it by chi prime. So this picture here shows you the Petersen graph and an edge coloring of the Petersen graph with 4 colors. And if you think about it, you can't do better. So its chromatic index is 4. Okay, so if we only look at edge colorings of graphs, then these are in some sense very well understood. For example, we have this old theorem of Vizing, which tells you that if we have just graphs, then the chromatic index is either the maximum degree or it's the maximum degree plus 1. So obviously it's at least the maximum degree, because if you look at a vertex and all the edges at this vertex, you have to color them differently. And the theorem says that you can always color all the edges with at most 1 color more than this. Okay? So sort of graphs are well understood, in some sense at least. Hypergraphs are harder. So if you look at the picture, we have a coloring of this hypergraph, which you probably can't really see. So we have 2 purple edges, 2 blue ones, and 2 green ones. Okay, but in general, the problem is hard. So even finding the largest matching in a hypergraph is NP hard. And this is in contrast to graphs. Okay, and here's the promised reformulation of the Erdős-Faber-Lovász conjecture in terms of hypergraphs. And this is about linear hypergraphs. And linear hypergraphs are hypergraphs of good degree 1. So remember, this means that whenever you look at two edges, either they are disjoint or they intersect in precisely one vertex. So you don't want to see edges which intersect in at least two vertices. So you have to forbid this. And then the conjecture says that if you have a n-vertex linear hypergraph, its chromatic index is at most n. So you can color all the edges with at most n colors. So Vizing's theorem actually implies this conjecture for graphs, because remember, Vizing's theorem tells you you can always color the edges with at most the maximum degree plus 1 many colors. And the maximum degree is for a graph always at most n minus 1, and so you can color the edges with at most n colors. Okay, now I will explain why the graph formulation of the conjecture and the hypergraph formulation of the conjecture are equivalent in a minute. But before I do this, let me give you 3 families of extremal examples which show that the conjecture, if true, is tight. So you can't improve the n here for the chromatic index. And the first class of extremal examples are pictured on the left here, and these are complete graphs on an odd number of vertices. So why is that? Well, you have n vertices, all possible edges in between, each of size 2, so you have a complete graph. So there are n choose 2 edges. Now, if you can color them with less than n colors, well, then every color class is a matching, but it must be perfect. So it must cover all the vertices. And this is just because you have so many edges. But if it's a perfect matching, well, then n has to be even. So if n is odd, the chromatic index must be at least n. So it's an extreme example. Okay, the second class of extreme examples are pictured in the middle here. So it's finite projective planes. So you can see a finite projective plane of order 2. And the edges are sort of indicated by the colored lines. So every colored line is an edge. So in particular, every edge has size 3. And so in general, a finite projective plane of order k is one where every edge has size k plus 1. So it's k plus 1 uniform. It's linear and it's intersecting. So this means that any two edges actually share a vertex. And it happens to have k squared plus k plus 1 vertices and also that many edges. So it has n edges. All of them intersect, and obviously, so you have to give each of them a different color. So the chromatic index is n. Okay, and the third class of extreme examples is pictured here. So it's what people call degenerate planes or near pencils. So again, we have n vertices, and n minus 1 of them lie in the bottom here. And they form one big hyperedge. So there is this blue large hyperedge of size n minus 1. And the remaining vertex sits at the top, and it somehow forms a size 2 edge, with each of the vertices at the bottom. So this is an intersecting hypergraph. So every edge intersects every other edge. It's linear, and it has n edges. And so you have to color each of them with a different color. Okay, so these are 3 sort of classes of extreme examples. And now, why are these 2 versions of the conjecture, or these 2 formulations of the conjecture actually equivalent? Well, in the talk, I only want to show you how you can derive the hypergraph version, so the version at the top, from the graph version, so the version at the bottom. So let's assume that we believe the graph version and we want to show that the hypergraph version is true. Okay, so we have an n-vertex linear hypergraph, so maybe the hypergraph here on the left, and we will use it to construct a graph. And what we will be doing is just we will look at the line graph of this hypergraph. So every edge of the hypergraph will become a vertex. Okay, so this blue edge of size 3 will become the top blue vertex in the picture of the middle. And for example, blue size 2 edge will become the bottom blue vertex in the picture of in the middle, and so on. Okay, so the edges become vertices. And now we join two vertices if the corresponding edges intersect, right? So for example, you join the blue vertex here with the purple vertex. If the two corresponding edges, which would be this blue edge of size 3 and the purple edge on the left, they intersect, so we join them. Okay. So this gives us our graph, and by construction, edge coloring of the hypergraph corresponds to a vertex coloring of the graph, and vice versa. Okay, now the graph which we have constructed is a union of n complete graphs. And why is this? Well, for every vertex in the original hypergraph, we get a clique. And these cliques here are pictured in the picture on the right. For example, if we look at this clique of size 4 on the left here, then this corresponds to the bottom left vertex in the hypergraph, right? And why is that? Well, at the bottom left vertex, there are these 4 edges and they pairwise intersect, so they form a clique. And these cliques have at most n vertices, of course, and each of them, every pair of them shares at most 1 vertex, and this is because the original hypergraph is linear. Okay, and if we believe the graph formulation of the conjecture, then we can color the graph which we have constructed with n colors, the vertices, and so we can color the edges of the original hypergraph with n colors. Okay, so this is one direction, and I spare you the other direction. Now, there was this more general problem where you intersect your complete graph, you allow to intersect your complete graph in at most t vertices instead of just in at most 1 vertex. So this was this more general question of Erdős. And similarly, as for the Erdős-Faber-Lovász conjecture, this has also a reformulation in terms of hypergraphs. So what you get is that you have an n-vertex multi-hypergraph. It has maximum degree at most n and could be at most t. And then the question is, what is the maximum possible value of the chromatic index? So these questions are equivalent. And there is the corresponding conjecture saying that the answer should be at most t times n. And here are one class of extremer examples. And these are t-fold projective planes. So basically you take a projective plane and then you take any edge and you, instead of one version of this edge, you add t versions of this edge. So you add any edge t times. Okay, so in the picture on the left, we have a threefold order 1 projective plane. And on the right, I didn't multiply the edges. So it's just a 1-fold projective plane of order 2. But a projective plane has codegree 1. So a t-fold projective plane will have codegree t. And its maximum degree will be t times k plus 1. And this is at most n if t is at most k. Okay. Okay, so we have seen the Erdős-Faber-Lovász conjecture and a reformulation in terms of hypergraphs, and similarly we have seen this more general question of Erdős, and a reformulation in terms of hypergraphs. Okay, so but what do we know about these conjectures? Well, let's just look at the Erdős-Faber-Lovász conjecture. So remember, and let's look at it in terms of hypergraphs. So remember, this means that you have an n-vertex linear hypergraph. And so you have to show that the chromatic index is at most n. And remember, linear means that any two edges intersect in at most one vertex. Then it's not hard to see that the chromatic index is at most 2 and minus 3. So basically, you get a conjecture in within roughly an additional multiplicative term of 2. And why is that? Well, order the edges according to their size. So start with the largest edge and the second largest edge and so on. And then now color the edges according to this ordering. So each time you give the edge you consider the, say, smallest possible color which is available. And then if you think about it, when you do this, you will be looking at some edge in your ordering. And then the question is, how many edges intersect this edge which come before in your ordering? And if you think about it, you will see that there are at most 2 and minus 4 of these edges. And so you can always color with 2 and minus 3 colors. Okay. And Chang and Lola improved this to roughly 3 and over 2. Okay, now here are 3 results which sort of relax the parameters. So the Kühn and Erdős theorem tells you that the conjecture is true if in addition you are talking about intersecting hypergraphs. And remember, intersecting means that you have any 2 edges, but you have to intersect in precisely one vertex since our hypergraphs are linear. And then the conjecture is true. Seymour showed that at least you can find a matching of the right size. And right size means total number of edges divided by n. Now, what does this have to do with the conjecture? Well, if you can color all the edges with n colors, well then, because every color class forms a matching, at least one of these matchings must have size total number of edges divided by n. And so Seymour's result shows that at least this consequence of the Erdős-Faber-Lovász conjecture is true. And Kahn and Seymour proved the fractional version. Okay, here are 2 results which heavily use probabilistic methods. Faber and Harris showed that the conjecture is true if in addition you know that every edge has size at least 3, and at most some constant times, some small constant times square root of n. And Kahn proved that the conjecture is approximately true in the sense that the chromatic index is not much more than n, so it's n plus little o of n. Our proof also heavily uses probabilistic tools, and as I said, we proved that the conjecture is true if n is sufficiently large. And we also showed that kind of there holds a stability result, which was actually predicted by Kahn. And this means that if you know in addition that your hypergraph is not too close to one of the 3 groups of extremal examples which I showed you, then you can do better. So let's look at this in a bit more detail. So again, we have an n-vertex linear hypergraph, but we have these 2 additional properties. And the first one is that the maximum degree of your hypergraph is not too close to n. And this forbids that you are close to a complete graph. And it also forbids that you are close to a degenerate plane, because both of them have maximum degree n minus 4. Okay, and the second condition is that if you look at the edges which have size roughly square root n, then you want that the number of these edges is bounded away from n. So it should be a little bit smaller than n, at least. And And this forbids you that you are close to a projective plane. And if you have these two additional properties, then the theorem tells you that you can do better. So the chromatic index of your hypergraph is bounded away from N. Okay, now let me tell you a little bit about the proof. So roughly speaking, the two main methods are random nibble, and we want to pair this with absorption. Okay, so what do we want to do? Well, we have this hypergraph and we want to color the edges. So we want to split the edge set into n matchings. And roughly speaking, sort of these matchings are more or less built randomly. So we will build each of these matchings in turn. And to build one of them, we somehow randomly edge suitable edges or eligible edges one by one. That's a bit lying, because actually you add small batches, small random batches, instead of adding the edges one by one. But the message is that if you look at these matchings or at our color classes at the end, then a big chunk of it is built randomly. Okay, but it turns out that this is not good enough, because we want our color classes to cover some desired vertices. And they won't do this if we just build them randomly. So each of the matchings which we construct randomly, we will then enlarge a little bit to absorb desired leftover vertices. So basically, in the end, we do some absorption step, which acts like a sponge. So we will absorb a few desired leftover vertices and making the random matchings, which we have constructed before, into our final color classes. So roughly, this is what we do, very vague. So let's make this a little bit more precise. Before we make this more precise, let me mention that one early success of the random nibble method is this theorem here of Pippinger and Spencer, which also has some consequences.
Daniela, I think we don't hear you anymore. One second. Now it's okay again. Try again.
Okay,
please.
sorry. So one early success of the Pippinger-Spencer theorem. Can you hear me?
Yes, yes. Now it's okay.
Of the Pippinger-Spencer theorem, no, one earlier success of the random nibble method is the Pippinger-Spencer theorem, which will have some consequences for the Erdős-Faber-Lovász conjecture. So let me state it here. So this is about hypergraphs of bounded edge sizes. So you know that every edge in your hypergraph has size at most some constant, some large constant maybe, but this constant is much, much smaller than the number of vertices. Okay, and then your hypergraph has maximum degree at most delta. But what you want is that the co-degree of your hypergraph is small in comparison to the maximum degree. So it should be little O of delta. And the theorem tells you that the chromatic index is not much bigger than delta. So it's delta plus little O of delta. So this is an approximate version of Vizing's theorem for such hypergraphs with bounded edge sizes, because Vizing's theorem, remember, tells you that the chromatic index is at most the maximum degree plus 1. And here you have at most the maximum degree plus maximum degree. And it generalizes Schröder's solution to the Erdős-Hanani conjecture about the existence of approximate combinatorial designs. This is where he introduced the random nibble method. Okay, now let me state 3 immediate corollaries regarding the Erdős-Faber-Lovász conjecture. So let's first look at the first one here. So the Pippinger-Spencer theorem immediately implies that the Erdős-Faber-Lovász conjecture holds if you know that every edge has size at least 3 and at most some constant k, where k is much smaller than n. And why is that? Well, how large can the maximum degree of a linear hypergraph be? Look at the vertex, look at all the edges at this vertex. Because the hypergraph is linear, well, these edges obviously intersect in your vertex, but otherwise they are disjoint. And because of this, the maximum degree of your hypergraph is at most this, this thing here. So n divided by the edge size -1, where you minimize this over all the edges. And so if you have that every edge has size between 3 and k, this means that the maximum degree of your hypergraph is at most n over 2. And so Spencer theorem tells you that the chromatic index is not much bigger than n over 2. So you have that Erdős-Faber-Lovász holds with room to spare. Similarly, if you look at this more general question, so the T version of the Erdős-Faber-Lovász conjecture, this holds if the edges have bounded size. In general, if you only know that the edges have bounded size and you look at the Erdős-Faber-Lovász conjecture, T is equal to 1, well, then you get from the Pipin-Spencer theorem that the chromatic index is not much bigger than n, because the maximum degree is, of course, at most n. Okay. Now, how does our proof work? Well, roughly speaking, the the reason why we have hope at all is the following. So look at any vertex. So either this vertex has low degree or it has higher degree. Okay, so far so good. But if it has low degree, this means that we have somehow flexibility at this vertex, because what we want is we want to split the edge set of our hypergraph into matchings. But if there are only a few edges at our vertex, then only a few of these matchings have to cover this vertex. And so in some sense, we have flexibility. On the other hand, if the vertex has high degree, well, it must look graph-like. High degree means degree close to n. But if your degree is close to n, then most of the edges at this vertex have size 2. This is because the hypergraph is linear, so the edges are disjoint outside the vertex. But as I told you, we know a lot about edge colorings of graphs. So the hope then is that somehow we can deal with this caseless plug. So this is the very rough sort of reason why we have hope. Now, let's actually tell you what we are doing, and let's only stick to this case when every edge has size 2 or 3 at the moment. So we have a linear hypergraph, but every edge has either size 2 or size 3. And our task is to show that the chromatic index is at most n. Okay, so what we do is we choose ourselves a set of k colors, and k is a little bit bigger than n over 2. And we want to partially color the hypergraph. So we want to color some edges of the hypergraph such that these 3 properties hold. Namely, every size 3 edge should be colored. Whenever you look at the vertex, at least half of the size 2 edges at this vertex should be colored. And every color class covers every high degree vertex, where again, high degree means degree close to n. So let's assume for a moment that we have found such a partial coloring. Then I claim that we actually are done just using Vizing's theorem. And this is because, well, look at the uncolored graph. It is a graph because we have colored every size 3 edge, so we only have size 2 edges left. And the maximum degree of this graph, crucially, is strictly less than n minus k. And why is that? Well, if you look at a high degree vertex, well, it's covered by every color class we have built so far, so it loses degree k. And it had degree n minus 1 at the beginning, and now at most And so it has degree strictly less than n minus k now. And for the low degree vertices, well, it had low degree before, and because of the second property, you can also show that it now has degree less than n minus k. But Vizing's theorem tells you that you can always color with maximum degree plus 1 many colors, and so you can color the leftover graph with n minus k colors. And so in total, you colored everything with n colors. This is what we want. So this is what we want to do. And as I said, we want to build our color classes by first doing a random nibble and then using absorption. And the random nibble will roughly give 1 and 2. Apart from it will only always almost give 1, but let's ignore this. We have to fiddle around it. And we will use absorption to satisfy 3. But because to sort of cover every high degree vertex. Now I'm lying a bit here because actually you can't achieve this perfect coverage property in general. So for example, if you start with a complete graph, every vertex has high degree. So in order to achieve this perfect coverage property, all your color classes must be perfect matchings. But if n is odd, you have a problem, of course. So we have to aim for something which is a little bit weaker, namely, we call it nearly perfect coverage property. And this means that every color class covers all but at most one of the high degree vertices. And on the other hand, every high degree vertex is covered by all but most one of the color classes. And then if you do the same thing, it still works, but you need one extra color. Okay, and you need some additional ideas to get from n plus 1 colors to n colors. So let's make this a little bit more precise. So we do in a little bit more detail. So first we have to define a set of high degree vertices. So this will be U, and as I said, high degree just means degree close to n. Okay, and then we will set aside a random reservoir of edges. And this will contain only graph edges, so only edges of size 2. And we choose it by choosing just every graph edge randomly with probability of 1. So this will be set aside. And now we aim to color the remaining edges. Using first a random nibble, and then by enlarging each color class into a slightly bigger matching, such that we can achieve this almost or nearly perfect coverage of U properties. So we want to cover all but at most one vertex in U. So here's our hypergraph. On the top we have the set U. So we will choose a few edges randomly. Some of these might intersect. We don't want them, so we ignore them, but the others we put in our color class. We look at the uncovered vertices. Again, choose some of the edges randomly. Ignore the ones which intersect and put the remaining ones into our color class. And we grow our color class like this until we covered almost all the vertices. Okay, but now we have to achieve that our color class covers all but at most one vertex in U. And we do this by using some of the random reservoir edges and Horst theorem. So if U is small, we find a sort of nearly perfect matching consisting of crossing edges, such that together with what we have built before, now all but at most one vertex of U is covered. And if U is big, actually we are choosing the edges inside. But in both cases, we add this small matching to what we have built previously, and this will then be our first color class. And then we choose the second color class by first doing random nibble, and then doing some whole argument using some of the random of the reservoir edges in order to achieve that our color class covers all but at most one vertex and so on. And this is the proof. Apart from the fact that, as I said, it only works if you have one spare color, one extra color. So how do you get from using n+1 colors to n colors, say in the case when n is even? But you can show that if you really need this extra color when coloring the leftover graph via Vizing, then your leftover graph is nicely quasi-random. And then you carefully remove a few more edges to make it also even regular. And then you can apply an older result of Deryk, Osthus, and myself, which shows that if you have such a quasi-random even regular graph, which is not too sparse, then it has a Hamilton decomposition. So you can decompose the edges into disjoint Hamilton cycles. Okay, but if n is even, then each of the Hamilton cycles can be split into two perfect matchings. So you have a one factorization. So you have actually a very efficient coloring. And so you don't need the extra color. Okay, so this was what we do if every edge of your hypergraph has size either 2 or 3. And roughly the same thing works if every edge of your hypergraph has bounded size. So size at most one big constant, which is much, much smaller than n. Now, let's look at the sort of other case when every edge has large size. So every edge has size at least some large constant. And here we want to use some reordering strategy, basically. And for this, we need this trivial fact. Look at any edge, and you are interested in the number of other edges which have size at least your edge E, and which intersect it. Because the hypergraph is linear, it turns out that the number of these edges is this quantity here. But because all the edges are large, this quantity is not much bigger than n. So it's n plus little o of n. Okay, and because of this, you can color greedily using the size monotone ordering of the edges to see that the chromatic index is not much bigger than n, right? So you, again, as I told you before, you order the edges according to their size, starting with the biggest one. And then you color the edges using this ordering. And then you are precisely interested in this number here. So you have an edge, you want to know how many edges have come before and are already colored and intersect this edge. Well, they are bigger, and so you have this number. And so you can color the entire thing with that many colors. But that's not good enough. We want to have n there and not a little bit more than n. So we want to find an ordering such that whenever you look at an edge E, less than n edges preceding E, because then you can use n colors in total. And we can show that either there is such an ordering, or we have structure, namely our hypergraph is close to a projective plane, or the line graph of this hypergraph is locally sparse, and then we use some well-known or some existing results at least about colorings and to finish off this case. So either we have our nice ordering or we use existing results because we have additional structure. Okay, so we can color these small edges using random Nibble plus absorption and finishing off by Vizing's theorem. And we can color the large edges using this reordering strategy. Both of them with n colors. So we've colored everything with 2 n colors, which is not quite what we want because we want to have n, right? So of course, you have to make sure that you can run these two cases in parallel, or so at least so that they don't contradict each other. So we will first be coloring the large edges via this reordering approach, achieving some additional properties. And then we color the small edges using the same n colors and make sure that we don't have any conflicts with the large edges. And the second phase is what I done, like I explained before, using a random nibble and absorption and finishing off roughly with Vizing. Okay, so this is all I wanted to say about the proof. So just let me finish with two open problems. First one is a conjecture of Beers-Furedi and Meinl, and it tells you that if you have a linear hypergraph, then its chromatic index is at most this quantity here. So what you do is you look at any vertex, look at the edges at this vertex, but you don't count them, but you look at the union of these edges, and you are interested in how big is this union. And then you maximize this over all the vertices. So here's a picture which shows you a hypergraph which has maximum degree 2, I think. So every vertex is in 2 edges, but this quantity is actually 5. So if you look at, for example, the 2 edges at the bottom left vertex, then they span 5 vertices. And so the conjecture would be a common generalization of Vizing's theorem and of the EFL conjecture. Because for graphs, obviously this quantity here is at most n plus 1, n. And for hypergraphs, no, for the EFL conjecture, for graphs, this quantity is at most the maximum degree plus 1. And for the EFL conjecture, if you look at this quantity, then obviously it's at most n. So it would imply both of them. And the final open problem which I wanted to mention is the list version of the EFL conjecture, which was conjectured by Faber. So basically it tells you that the EFL conjecture is true if you look at list colorings. And list colorings means that for every edge you have a list of available colors of size at least n. And then you have to find a proper edge coloring, but you have to make sure that every edge is colored with a color of its list, in its list. And if you make all the lists the same, then this gives you the EFL conjecture. And another thing which I wanted to mention is that if you look at the methods of Kahn, then you get an approximate version of this. Okay, so this is all I wanted to say in my talk. So thank you very much for your attention.
Thank you very much, Daniela, for this very colorful and very pedagogical talk. Any questions?
Thank you, wonderful. And I wanted to ask, you showed us how the original formulation of the conjecture implies the hypergraph formulation. Could you say something about the reverse implication?
I can say something, but maybe I actually back to the slide with the pictures. Oops. Yeah. Okay, so so I said you want to do it the other way around, right? What I explained is happens if we believe the original formulation and want to show the hypergraph formulation. This is what I explained in the talk. So I think you are asking me to do the other direction, or should I explain the direction I did before again?
Yeah, how the hypergraph formulation implies the original.
Okay, so now we So now we are saying that the top version holds, and we want to derive the bottom version. So we are given a graph and somehow want to construct a hypergraph. And basically, the graph is a union of clicks, and every click will become a vertex in your hypergraph. Okay, so you have vertices 1 up to n, say, and now you have to define how you define the edges, and basically every edge of your hypergraph will correspond to an intersection of 2 clicks. So if you look at a vertex which is in the intersection of clicks, well, it will be the intersection of, say, 5 clicks. And then in the hypergraph, you draw a hyperedge consisting of these 5 clicks. Okay, so this is how you construct your hypergraph. So again, the vertices are the cliques, and the hyperedges basically correspond to the vertices in the intersection of cliques. Okay, and now we want to color the edges of the hypergraph. We get from the graph version, we get a coloring of the vertices of the original graph. And so basically we have colored also the vertices in the intersection of cliques. But the intersection of cliques correspond to the hyperedges, so we have colored the hyperedges. And now you only have to check that actually the hypergraph which you are getting is linear, and this is because every two cliques only intersect in at most one vertex. And it has n vertices, of course, and that's all.
Just a curiosity, do we have a good idea of for how large a value of n the proof techniques go through? And for small values of n, do we have any pathological examples?
For smaller values of n, we basically only have these results which I showed you. Our proof uses a lot of probabilistic tools, and so you have to make sure that the estimates are going to hold. And the additional sort of results we will be using. So for example, the result which I showed you, which brings you from n+1 colors to n, actually also use the irregularity lemma, so n will be huge. It will be really huge. So we never calculated it, but it's really massive.
Thanks.
Okay, let's thank Daniela again.
Okay, thank you very much.
Thank you very much.